class. This is Mrs. Brunk. Welcome to Module 12, Introduction to Sequences and Series. We're going to take a little break from the textbook and use some supplemental materials to teach you a little bit about sequences and series. And that just so that we found that these materials are a little more consistent with the course that comes after this, which many of you will be taking, and so we wanted to make sure we were kind of teaching in line with kind of what in mind those things that are going to be coming regarding this topic in courses to come. So this will really constitute Module 12, but the resources that accompany our textbook will just be a little bit different. They'll be won't follow the exact path. We're going to start off today by looking at sequences, and we're going to define what a sequence is. We're going to look at both finite and infinite sequences, and we're going to learn how to generate some sequences. But let's start off with what a sequence is. So a sequence is a set of numbers with a particular order or pattern. Each number in a sequence is called a term. Now, a finite sequence is actually a sequence with a limited number of terms. A very simple example of a finite sequence might be 1, 2, 3, 4, 5. So that would be a finite sequence of just 5 terms. Now, on the other hand, a sequence that is infinite would be a sequence with unlimited terms. In other words, they're not ending. And a very similar example for that would start off like the other finite sequence, 1, 2, 3, 4, 5. But then if I put a dot, 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 meaning it's going on like this forever along this pattern, that would actually be an infinite sequence of the natural numbers. And then again, the natural numbers are actually the numbers that we naturally count with. The difference between that and the whole numbers would include 0. So whole numbers would be 0, 1, 2, 3, 4, 5, dot, 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 and that would go on forever. That is also an infinite sequence. But with the natural numbers, it does not include 0. So that's an infinite sequence, one that goes on forever that has no end. Now, we use a lot of really special notation when we work with sequences and series, and so we're going to look at a little notation here. So when we identify the very first term in any sequence, so like in the case of the ones that we looked at here, the first term was 1, but we denote that as A sub 1. So that little subscript 1 means that's the first term in the sequence, and each subsequent term we will notate it as A sub n, where n is the number that the term represents in the sequence. So like n sub 2 would be the second term, n sub 3 would be the third term in the sequence, and so on. So just identifying the terms, so A sub 1 in this sequence of 1, 5, 9, 13, 17 would be 1. And the fourth term, which is the next one they're asking for, A sub 4, would be 13. A sub 9, well, let's see if we can identify the next terms in the sequence, because A sub 9 is not listed here. So let's see if we can figure out what's happening, and we'll kind of generate the rest of this sequence. So from 1 to 5, that's going up 4. Or alternatively, it could be multiplying by 5, but when we look at the next term in the sequence, that is also going up by 4. So this looks like what we would call an arithmetic sequence, also sometimes called a linear sequence. So it's going up by a set amount, kind of like a slope. And so I've got 1, 5, 9, 13, 17. The next one would be 21. The next one would be 25. The next one would be 29. The next one would be 33, and then 37. Next one is 41, 45, and so on. And let's see if we've made it to all the ones we need. So we needed a sub 9. So we have the first one was 1, then 5. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. The ninth term is 33. Then 10, 11, 12, and the 12th term is 45. Now, since each term value is paired with exactly one number, a sequence is a function with the following properties. The domain is the set of natural numbers. So those ones we said that, or the term numbers, and so sometimes we'll say the domain is natural numbers, but you could also say term numbers. And we usually say that for a finite sequence because maybe we have a subset of the natural numbers. So see here we only have from 1 to 5, 1, 2, 3, 4, 5. If we didn't know that this pattern was going to continue going on, we would say term numbers. But if it was infinite, then we would say natural numbers for the domain. And then the range, which is always the output, that actually is represented by the actual terms that are in our sequence. So they are the term values. So we're going to be looking at two different kind of sequences. The first one is called a recursive sequence or recursive formula. And what a recursive formula is a rule or formula sequence in which one or more previous terms are used to generate the next term. In other words, if we want to say get the third term, maybe we have to add the first and the second term, or maybe we have to subtract them, or so there'll be some relationship from of a term to some terms that are prior to that. Now, I'm sure that the most famous recursive formula is the Fibonacci sequence. I can't imagine there would be one more famous. And maybe you've heard of it before. If not, I really encourage you to go to Google that, look it up. But it is considered to be one of the most important sequences and it is definitely reflective in nature. So you see this pattern of numbers we're going to look at right now, really found in so many places in nature. So very important. And that is a recursive sequence, and it's actually a sequence that is the sum of the two preceding ones. And so it actually starts off with the number 0, and then the next term is 1, and so is the next term, and the next term after that is 2, followed by 3, and 5, and 8, 13, 21, the next one's 34, and so on. And this is an infinite sequence. It goes on and on forever. And so one of the things that makes this so special is, again, it's this pattern of these numbers really you'll see kind of repeating in nature in some really cool ways. I'm sure we'll look at that a little bit more. But the other thing is that the ratio between sequential values, so in the sequence, is approximately the golden ratio. So if you divide each of these terms by the prior term, you get this golden ratio, which is kind of famous in architecture, and it's considered to be the ratio of great beauty in architecture and things. So if you study art, you may have heard of the golden ratio. So the Fibonacci sequence is a sequence that, again, it's taking two terms, and so of course you'd have to start off with knowing the first two terms to generate the third term. So that third term right here, this second one, is actually generated by adding the two numbers that are prior to it. So adding the 0 and the 1. And of course that works with the next two, so the 1 and the 1 add up to 2, the 1 and the 2 add to 3, the 2 and the 3 add to 5, the 3 and the 5 add to 8, and so on, and that generates that Fibonacci sequence. Now sometimes recursive sequences depend on just one prior term and then doing some operations to it, some more and more complicated. But in this case it's really a simple strategy to get terms in the sequence. You just have to go find the two prior terms and add them, which means in order to give a rule for this sequence, you would have to be given the first two terms. And so we would have to know that a sub 1 was 0, and we would have to know that a sub 2 was 1. And so if we wanted to write a rule for that, it would look like this. A sub n, meaning any term in the sequence, would be equal to, and so like the second term is actually the third term is the first and the second put together. But if we wanted to generalize that, we could say that the nth term is the term before it, which would be the a sub n minus 1. That means 1 before that, plus 1, 2 before that, which would be n minus 2. So that would be a little rule that would describe this Fibonacci sequence. So you could take, if you're trying to find the third term, you could take the second term and the first term. If you're trying to find the 10th term, you would take the 9th and the 8th term. And so again, these subscripts just, it's basically kind of directing you which terms prior to add. So we're going to start off first just generating terms in a recursive sequence. And so let's take a look at this first example. So they want us to give the first 5 terms, which really means in this first one, we are going to have to generate 4 more terms, because they gave us the first term already. The first term was 14, and I can see that right here. And so then what they want me to do to get the the following term is to add 9 to whatever the prior term is. So that rule for that second part of the sequence is a sub n is equal to a sub n minus 1, meaning the prior term, plus 9. And if that really helps, you can kind of think about just crossing this part off and actually saying prior term. That's really what that notation means. It's read prior term. So to get the next term, I would just have to add 9 to 14, which makes 23. I'd add 9 to 23 to get the next term, which is 32. I'd add 9 to the 32 to get 41. And they wanted 5 terms, so 1 more, add 9 again, I get 50. Now with the next one, they want me to, again, generate, and just to kind of clarify this notation here, this is saying for n greater than or equal to 2, and that means because to generate, in other words, the second term and up, because we already know the first term in this case, so the first term is the 6, and I know that the next term, I'll have to take this term that's 6, multiply it by 2, which makes 12, and subtract 5, which gives me 7. So to get the next term, now I'm going to take that 7 and I'm going to plug the 7 in. I'm going to multiply it by 2, which gives me 14, and subtract 5, which then gives me 9. Now I'm going to take the 9 and plug it in. 9 times 2 is 18. 18 minus 5 is 13. And now I'm going to plug 13 in. 13 times 2 is 26, minus 5 is 21. So notice that in these sequences, there's not this always this consistent change. Now in the first recursive sequence, you could see that each term was just 9 more than the prior. But there's not this set sum or difference between the terms in the second example, because between the first two, there was a difference of 1. But then between the next two, it was 2, and the next one, it was 4, and then the next one, it went up by 8, and so on. So there wasn't this predictable pattern that we could have just used to generate the next term. We really had to use the rule that they gave us, and that was taking the prior term, doubling it, and then subtracting 5. Let's go ahead and turn the page and see what comes next. So here's another recursive formula. They want us to generate the first 5 terms, and they want us to find that for n is greater than or equal to 2. In other words, they want us to find the second term, the third term, the fourth term, and so on, because they already gave us the first term, which is 354. So what they're wanting me to do, and this is where I'm going to have to probably break out my calculator, but on this one they want me to take that first term, 354, they want me to add 6 to it, and then whatever I get, they want me to divide by 3. Well, when I add 6 to it, I get 360. Divide by 3, I get 120. So my next term is 120. Then to get the next one, I'm going to take the 120, and I'm going to add 6, which gives me 126, and then I'm going to divide by 3, which is going to give me 42. The next one would take 42 and add 6, which is 48, and then divide by 3, which is 16. And now we've got 4 terms. We need one more to satisfy the directions. And so we're going to take that 16, we're going to add 6 to it. Again, we're going to keep just taking this 16, plugging it back in for the a sub n minus 1, which again really means prior term. And again, if that helps you at first as you're getting used to this, if you want to cross off that a sub n minus 1 and write prior term. Oops, hold on. Or you can use the phrase prior or previous term. So now I'm going to take that 16. I'm going to add 6, which is 22. But this time when I divide by 3, that's not going to come out nice. That's 7.3 repeating. So I could either write it as 22 thirds or 7 1/3. And that's the fifth term. So again, that's the first was 354, excuse me. And so this is first, the second, the third, the fourth, and the fifth term. And remember, this represents n, and each of these represents a sub n, some term in the sequence. So that first row is like your domain, and that's telling you the number that of the term is in the sequence, and then the range or the output is actually telling you what those terms are. So we'll look at one more. Now this time the sequence, the recursive sequence, gives you 2 terms. And so they give you the first 2 terms, and we're going to generate 3 more. So I have the first term is 3, and the next term is 4. And now this rule is going to tell me what to do with those terms. And it says to get a sub n, you're going to take a sub n minus 1 and multiply it by a sub n minus 2. And so what that means is I'm going to take the 2 prior terms. So I'm going to take these 2 terms here, 3 and 4. I'm going to multiply them in order to get the next term. And then I'm going to do that again. And this time I'm going to be multiplying 4 and 12. I'll multiply them. And this time I get 48. And so these numbers can get pretty big pretty quick. And then the next time I'm going to multiply the 12 and the 48 to get the 576. Now in the next 2 examples, we're going to see if we can write our own recursive rule. And typically when you do that, you use some kind of fancy brackets like this, and you'll start off, I mean, it's a little different than how they did it here, but how we usually do it is we'll list the whatever the given terms are first. So in this case, they're all having them based on, it says write a rule for each sequence, then give the next 3 terms. And so my first term here is a sub 1, and it is actually 4. And as far as writing this rule, it's kind of just like at this point, like later on we'll learn some strategies based on what kind of sequence if we know what it is. But right now it's kind of just looking to see if we can see that pattern, and we can see if we can, try it out. And if it works, then we use that as our little equation. So somewhat think I can do to 4 to get 11. Well, I could add 7, but then I look at the next sequence, and if I take 7 and add, or 11 and add 7, I get 18. So that doesn't generate the next term. And so I think, what about if I took, I know that 11 is really close to 12. So if I took 4 and multiplied it by 3, that would give me 12. But then I'd have to subtract 1. So let me see. I'm gonna see if this will work. So if I took 3 and multiplied it by the prior term, which again we call a sub n minus 1, and that would be, so if I'm trying to find a sub n, which is whatever term in the sequence I'm looking for, I would have to take 3 times a sub n minus 1, or the prior term, and then subtract 1. Now let me see if that works. So let's see. 3 times 4 is 12 minus 1 is 11, so that worked. The next one, now I have 11, so if I take 3 and multiply it by 11, I get 33, and subtract 1, that gives me 32. Okay, I'm on a roll. 32 times 3 is 96, minus 1 is 95. Bingo. We've got our sequence. This is our rule for it. And if we want to generate the next 3 terms, so we just have to take now 284, and we're going to multiply it by 3, and I get 852, and then I'm going to subtract 1, which gives me 851. So the next one is 851. I'm just going to write them here in this margin since I've kind of run out of space. Then I'm going to take the 851, I'm going to multiply it by 3, and I'm going to subtract 1, and that gives me 2,552. And now I'm going to take 2,552, I'm going to multiply it by 3, and I'm going to subtract 1, and that gives me 7,655. So let's try another one. Let's try 6. So this time I start off with 100. So when I'm using my notation, and again I kind of use this usually, that fancy bracket is how you usually see it done. The first term is 100 here. Now I got to find a way to generate the next terms. So from 100, then I go to 60, which, let's see, that goes down 40, but then that doesn't work for the next one because then it goes down 20. But then the next time it goes down by 10 and then down by 5. But I got to find a way to make that something that's consistent rule as I go along. So let's see if there's a way. So if I took the first term, which is 100, and I multiplied it by a half, or let me cut it in half, which is 50, and added 10, I'd get 60. Let's see if that works for the next one. If I take 60 and I cut it in half, like multiply it by half or divide it by 2, I get 30, and then add 10, I get 40. Okay, so far that's working. Then I take 40, divide by 2, or multiply by a half, in other words, that's 20, add 10, I get 30, bingo. And then take the 30, divide by 2, which is 15, and add 10, that's 25. So it works for all of these. So what it looks like I'm doing to get the nth term, and again, this is just sort of looking for a pattern, is I am multiplying, or I guess dividing by a half, but I'm multiplying, or dividing by 2 or multiplying by a half, the prior term, so a sub n minus 1, I'm multiplying by a half, and then I'm adding 10 on after I do that. And that works to generate all these terms. So let's see if we can generate the next two terms, or actually next three terms. Actually, in this case, I'm not going to do that, just in the interest of time. And those numbers are not really nice because you can tell half of 25 is going to be 12.5. Or I'm sorry, yeah, 12.5, and then add 10 is 22.5, and then so on. So we'll maybe just give one more. It would be 22.5, and then they get kind of bad after that. But that would be the next term. Now here is the big issue with recursive formulas. And sometimes that's all you can do. Like the Fibonacci sequence, or, it's kind of notoriously, recursive, but a lot of sequences, you'll be able to write what's called an explicit rule. Recursive rules really depend on you knowing prior terms. So like, let's say you want to find the 1,000th term for this sequence, we would need to know the 999th term, right? And that's very cumbersome to have to generate that sequence all the way up to 999th term so that you can then apply that term to the formula to get your 1,000th term. So if we can, we really like to count on explicit formulas. So what is an explicit formula? It's a rule in which the nth term is defined as a function of n. In other words, because it's a rule in which the nth term is defined as a function of n, it doesn't depend on knowing prior terms. So if you want to find that 1,000th term and you have an explicit rule, there's a place in that function that you can just plug or substitute in 1,000 in for n, and you'll be able to directly calculate that particular term in the sequence. And so, explicit are like direct formulas. You can just kind of like, linear equations, when they're defined in terms of x. Well, this is defined in terms of n. And if you want to know the 5th term, you plug in 5. You want to know the 10th term, you plug in 10, and so on. So this one, they want me to, in this section, they want me to look at some explicit rules and generate the first 5 terms. So this is what a typical explicit sequence looks like. It really is just an equation. A sub n is equal to 7 times n minus 3, where you just literally plug in numbers in the sequence. So I want to find the first term, I plug in 1. So if I input 1 minus 3 is negative 2, times 14 is, times 7 is negative 14. Sorry, I'm getting ahead of myself. Then if I plug in to get the second term, so sometimes when you represent these, you may want to just kind of label which term you're at, but that's really not necessary. You can always count, but then you don't lose track of where you're at. So plugging in 2 minus 3 is negative 1, times 7 is negative 7. To get the third term, you're going to plug in 3 minus 3 is 0, times 7 is 0. plug in 4 to get the fourth term. 4 times minus 3 is 1, times 7 is 7, and then 5, plug in 5, 5 minus 3 is 2, times 7 is 14. So that's that explicit rule here where we can just substitute values in. We'll try a couple more of these, and then we'll have a few of these as you try questions. So we'll definitely do 8 together because, it's got a fraction. So the rule is for 8, it says to take 1/3 and raise it to the n plus 1 power. So again, in where n was in the recursive formulas, n was a subscript. There's no operation with subscripts, right? But here, this is an exponent. So we're actually going to plug a number in there that will create an exponent, and then we just raise 1/3 to that power. So substituting in 1 would really mean that I would be taking 1/3, and I would be raising it to the 1 plus 1, or the 2 power. And so my first term, so that would actually be, oops, I'm going to just write it as 1 plus 1. So that first term would come from taking 1/3 and squaring it, and so my first term is 1/9. The next one would be raising 1/3 to the 2 plus 1 power, which is the third, and that's 1/27. And then the next one would be to the fourth power, that's 3 plus 1, and that's 1/81. You kind of see that pattern. We're basically we're squaring the top, but not squaring the top, but raising the top to different powers, sequential powers, and but that's just still 1, but the bottom one is just going to higher and higher powers of 3. So that next one would be 1/243, and then the next one is 1/729, which would be 1/3 to the 5 plus 1, or 1/3 to the 6th power. So we're going to take a opportunity here to have you try some you-try questions, and I'm going to have you try 9, 10, and 12. We'll come back and do 11 together, but please pause the video now, and we'll designate 9 and 10 and 12 as the you-try questions, and those, they want you to generate the first 5 terms. So go ahead and pause the video now, use the explicit formula to generate the first 5 terms. Okay, so take a look at your answers to 9, 10, and 12. And be sure to make a note if for some reason you were struggling with any of those, and you can bring them up when I see you in class. So let's go ahead and finish up these examples by doing number 11. So the only reason I really wanted to do number 11 with you is I just wanted you to be really cautious about the fact that the base here that we're going to be raising to different powers is a -2. So, like for instance, to get the first term, I'd be raising -2 to the 1 minus 1 power, which is -2 to the 0 power. Of course, anything except for 0 to the 0 power is 1. But then say the next one, now I'm going to be raising -2 to the 2 minus 1, which is the 1 power. Of course, that's -2. But then the next one, I'm going to be raising it to the 3 minus 1, which means I'm raising -2 to the second power. So remember, with the parentheses, the negative is also being squared. So that's squaring -2, which is going to make +4. And then the next one is going to be raising to the 4 minus 1, and that's 3. So -2 to the third power is -8. And then the next one would be -2 to the 5 minus 1, which is 4, and that's +16. So you can see these are alternating signs, and based on whether the power is even or whether the power is odd. Now this first example in this next section is we're going to spend a lot more time on it. We're going to actually have an entire lesson devoted to this type of sequence. This is actually an example of a arithmetic or linear sequence. And how I know that is I can see that each one of these terms is actually not increasing, by 2, but decreasing by 2 every time. I see that there is a consistent change. So generating terms, if this was defined recursively, or defining this recursively, would actually be very easy. I would just say I'd take the prior term and subtract 2. But how do I write that when I need an explicit one? Because I need to have something that I can plug 1 in and get -7. I need to have something I can plug 2 in and get -9. And so what I really do is I really think about this more like it's a linear function. And I know that when I write a linear function in y equals mx plus b form, so y equals mx plus b, I'm going to kind of relate it back to this, is, you know, that the slope is the constant change. Well, I can see what the constant change is. That constant change is -2. But the b is actually the y-intercept, which in this case would be like finding the the zero term. See, I have the first term. So, but if I were to work backwards a term so that I had the zero term, it would actually be -5. And that's like the y-intercept in slope-intercept form. And so a rule, an explicit rule that would work for this, which again I define as being a sub n, would relate, and so instead of using x, I just use n, would take -2, multiply it by n, which means the number in the term, and then subtract 5. And we can check to see if this works. If I take a negative, say, 11, and I want to get that as the third term, if I plugged 3 in, that would be -2 times -3. I'm sorry, -2 times 3, not -3. The third term would be -6 minus 5 is -11. So same thing, I could plug in 4, that would be -2 times 4, which is -8, minus 5, that's -13. And so you can see it's generating those terms just by simply plugging in what term in the sequence it is. So now they wanted the next 3 terms, and so they've got the first 5, so they've plugged in up through 5. Now if I plug in 6, -2 times 6 is -12, minus 5 is -17. And I can actually just see, I mean, they're now going down by 2 each time, so I could just do -17, -19, -21, and I could have really done that without having the equation, but of course the equation is going to help if we have much higher number terms in the sequence that we want to find. So this next one is kind of, again, it's just, there's not really like a specific way that we know yet how to figure out these patterns, but I can certainly tell that this one is not like the number 13. At first it starts with 3 and it goes to 6, so it's either going up by 3 or multiplying by 2, but then when I get to the next term, it's not going up by 3 or multiplying by 2, so it's not anything that has to do with that. So that's not working. And then like the next term from 11 to 18, now it's going up by 7, and then it's going up from 18 to 27 by 9. And so there's not really anything going on there. So I start trying to think about some other kind of patterns that I might see. And what I see is that, at first I see that 3, and then I see that 6, that 11, and I don't know, like, something just kind of is triggering in me. I almost feel like it has something to do with perfect squares. Because all of these numbers are really close to a perfect square. You know, the perfect squares are 1, 4, 9, 16, 25. Each one of these terms looks like it is 2 more than that sequence right there. So again, this is kind of like there's, not a specific way I'm finding this. I'm just kind of looking and see if I can figure out the pattern. And so I'm thinking what would work is taking n, the number in the term, and squaring it, and then I would add 2 to it. And it actually works for every single term that I see listed here. So my best guess is this is the sequence. So then that would mean the next one would be taking 6 and squaring it, and then adding 2. So that would be 36 plus 2, which is 38. The next one would be taking 7, squaring it, which is 49, and adding 2, that's 51. And then taking 8 and squaring it, that's, hold on just a second. So that would be taking 8 squaring, that's 64, and then adding 2, which is 66. So that this next one, number 15, that's starting to look even more tricky, because now it looks like it's like got some nice integer values, but then there's some fractions in between. But if you look at the 5/2 is just 2.5, and then that's really 2, 2.5, 3, 3.5, 4. So the next term I'm sure is 4.5, but because they're writing it in fractions, they're using 9/2, and then the next one would be 10 halves, which is 5. Oh, so now you see the pattern, because what this really is, this first one would be like putting 2 over 2. So let's 2 over 2, I'm sorry, hold on just a second. I'm going to write this, 2 over 1, sorry. If I put this as a fraction and then I put this as a fraction, I'm going to put these as all as fractions, but make the whole numbers over 1, then maybe I can see that pattern a little better. So first I started with this. I said 2 over 1, because that's what 2 is, and then 5 over 2, and 3 over 1, and then I said 7 over 2, and that was kind of just not, I wasn't seeing that pattern there, so then I thought, well, what about if I wrote 2 over 1 instead with the same denominator of 2, and so to make that 2 would be 4 over 2. Okay, well, that would work. Let's see if I could do that with the next one. So 3 over 1, if I wrote it as 6 over 2, then it would still be 3. Oops. And then it would be 7 over 2. Then it would be 8 over 2, which would be reduced to 4, and so on. So now I'm kind of seeing that pattern. That makes sense that the next one would be 9 over 2, then 10 over 2, which makes 5, and then the next one would be 11 over 2. So getting the terms, I get that. So sometimes when this is the case, it might actually be easier to, instead of trying to write the entire formula for each term, but instead of maybe looking at the numerator and denominator separately. When I do that, I can see that the denominator of this sequence is just a fixed number. It is just 2 every single time. It doesn't change. But the top looks like one of those little linear sequences that we had in 13. And it looks like if I worked backwards, 1, and since I went 4, 5, 6, 7, 8, if I'm going backwards, this would be 3, right? And but then from there on, it's going up by 1. So if this was kind of like in slope-intercept form, if this was like my y-intercept, this would be plus 3, and my slope is changing by 1, so it would be like 1x, right? So it would be like x plus 3, or in this case n, 1n, or n plus 3 over 2. And that actually works for every one of those terms. So again, that was kind of a strategy. When I see that happening when there's fractions like that, I try to write them all that way, and then see if maybe I can describe the numerator and denominator separately. So that would be a formula that would work for this one. Now this next one, it looks like it's a little bit intimidating because I see some square roots and stuff, but also I can see like the first one is 1, then the square root of 2, then the square root of 3, and then the next one turns out to be 2. Well, I happen to know that if I square root 1, I get 1. If I square root 4, I get 2. So this is really like saying the square root of 1, which is 1, then the square root of 2, the square root of 3, this is the square root of 4, then the square root of 5. So then I'm thinking the next one would be the square root of 6, then the square root of 7, then the square root of 8. Now if I got to the next one, so let's do one more, the square root of 9 would make 3. So it's just taking whatever number in the term we are and square rooting it. So it'd be square root of n. Now the only thing with this next term right here, this square root of 8, we might not want to leave it like that. Maybe we want to rationalize or simplify it down to 2 square root of 2 by taking out the square root of 4. But still, the square root of 8 really makes the emphasis on the fact that it's just square rooting the number in the sequence. Okay, let's go ahead and turn the page. So the next thing we're going to look at was the other thing we said this was an intro of. We said this is an introduction to sequences and series. So what exactly is a series? Well, a series is just the expression formed by adding the terms of a sequence. So for instance, for this finite sequence, 1, 2, 3, 4, if I were to add those together, I would get 10. So what about this next sequence? How could I find the series there? Well, that's 3, 6, 9, 12, and the dot, dot, dot means it's going on, and it goes on infinitely, right? Following this pattern. So I don't really know how to add all those up. I mean, how can you do that? I mean, there's an infinite number of terms. So what we're going to look at today is what are called partial sums. So maybe I designated you to find, say, I wanted you to find the first 4 terms. So you'd add up the first 4. Maybe I wanted you to find the first 10 terms. So now you have to generate more terms and then see if I was able to, kind of, get out to the 10th term and add those up. So we're going to be looking at partial sums today. So let's say in example number 1, I wanted to find this S sub 9. What that really means is that I want to find the sum of the first 9. So this is the first 9 terms I want to add up. Well, let's see what the pattern is. I've got 1, 2, 3, 4. Ooh, I can see that. 5. Oh, the next one's 6. The next one's 7. Let's see, that's the first, second, third, fourth, fifth, sixth, seventh, eighth, and ninth term. And so those are the first 9 terms. I'm just going to simply add those numbers all up. And that's how I change it from a sequence to a series, is I take out the commas between the terms and I put the pluses in because I want to add them all up. So I'm going to add all of these terms and see what I get. And these add up to 45. In number 2, they want me to find the sum of the first 4. So I've got the first 4 terms. They're right there. I just have to add them up. I have to add the 4 and the 7. So if I wanted to find S sub 4, just add the first 4. 4 plus 7 plus 13 plus 25. So notice we're using S's instead of A's. So S means the sum of the series of the first 4 terms in this case. So 4 plus 7 plus 13 plus 25, and that's 49. So S sub 4 is 49. So I'm going to go ahead and designate the next 2 to be U tries. You give these a try. This one I want you to find S sub 6, and this one S sub 3, and I know there's some fractions there, but you just have to add the first 3. So you're just going to take the first 3, add them up, and then this next one you're going to take the first one you're going to have to generate one more term so that you can find the first 6 terms sum. So go ahead and pause the video now and try 3 and 4 for you try. So hopefully you recognize that this pattern was the perfect squares, 1, 4, 9, 16, 25. So the next one was 36. And then we add up the first 6, and that's 91. So 91 would be the sum of the first 6. S sub 3 would be adding 1 and adding a half, and then adding a third. And of course we would need common denominators for that. And hopefully you got 11/6. Or you could also say that's 1 and 5/6. No particular format we need to have it in. Oh, they are expressed as fractions, so 11/6 is fine. You definitely don't want decimals if the terms in the sequence are fractions to begin with. So next we're going to talk a little bit about what's called summation notation. So summation notation is like a different way to indicate what the sum is that you want, and instead of giving the actual terms, they'll give you an equation that describes the terms, which is basically like an explicit formula that's going to describe the terms in that sequence. And then through this notation, it'll tell you how many of them they want you to add up. So in this way, they can use this notation to maybe say, well, maybe I don't want to add the first 5 terms, but maybe I want to start at the 8th term and I want to add up to the 12th term or whatever. So this nth equals 1. This is the sigma is a summation notation. And the n sub 1 that's underneath it is telling me this is your start value or your start term, right? You're going to start at the first term. And then whatever number's on the top, that's your stop or your end term. So in this case, they just want us to find, with this notation, the term from the first to the 5th term. And the explicit formula that generates those terms is 2n. So you could start generating the terms in that sequence. So you could plug 1 in, which 2 times 1 is 2. Then you could plug 2 in, which 2 times 2 is 4. Then you can plug 3 in, which is 6. Then you can plug 4 in, which is 8. Plug 5 in, which is 10. And we're going to stop because we were only going to go up to 5, remember? That was the end. And so then we're going to add these all up. That'll be our sum. And so that's going to tell us to find, so again, this is your explicit formula. Explicit. Now all we have to do is add these up. So we're going to add the 2 plus the 4 plus the 6 plus the 8 plus the 10. And that adds up to 30. So this would equal, if I was writing this out in this notation, I'd say it equaled 30. So we're just going to try a couple of these, and I think that'll get us set for trying these for our homework. So here's an example. This one wants me to start at the first term and end at the 12th term, and the sequence is found by taking whatever term in the sequence it is and subtracting 1. So if I were to plug in 1, it would be 1 minus 1, which is 0. Then the next one would be 2 minus 1, which is 1. The next one would be 3 minus 1, which is 2. And so you can see all that's really going to happen is it's just going to be 0, 1, 2, 3, 4, and so on. And so my last term, when I add these up, so 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and my 12th term would be 11 because it would be 11, or 12 minus 1, which is 11. So now we just have to add up those numbers, and of course we can use a calculator. So add those up and you get 66. Let's try another one. So this one is going to start at the first term, and then, so we're going to start plugging in 1 and then 2 and so on, and then we'll end at the 7th term. Sometimes it just kind of helps to, keep track. This is the first term. So when I plug in 1, that's 1 times negative 3 is negative 3, then 2 times negative 3 is negative 6, and 3 times negative 3 is negative 9, and then 4 times 3 is negative 12, 5 times 3 is negative 15, 6 times 3 is negative 18, and 7 times 3 is negative 21. So, and again, I'm going to add all these up, and so find the sum. And that's negative 84. So again, using that notation, we would say something like this. We could write that summation notation for n equals 1 to 7 of negative 3n is equal to negative 84. Let's turn the page and maybe try one more before we end. So you'll get, we can come back to and do some of these more as some extra practice, but we'll just do one more because I think we're kind of getting the hang of it. So let's take a look at number 10. So number 10, I like that. That was interesting because that was one of the first ones I saw that didn't start at the first term. Actually, the number 8 didn't either. But what that really means is that, so we're going to start off and we're going to first plug in 2, and we're going to plug in, so this will be the term, 2, 3, 4, 5, 6, 7, and 8. So we'll find the second, the third, the fourth, the fifth, the sixth, the seventh, and the 8th terms. And we do that just by plugging in 2, 3, 4, and so on. So what they want us to do is cube the number c. And again, they're using c here, but you can see on the subscript there they did c equals 2. So they're just using c instead of n. They want us to cube the number and divide by 2 and then generate these terms. So I'm going to take a second and fill those in. So I know that 2 to the third is 8 and divided by 2 is 4. 3 to the third is 27 divided by 2 is 13.5. 4 to the third is 64, and then if I divide that by 2, I get 32. If I take 5 to the third, that's 125. Divide that by 2, that's 62.5. If I take 6 to the third, and that is 216, and then I can divide that by 2, and I get 108. And then take 7 to the third, and that's 343. If I divide that by 2, I get 171.5. And then finally, 8 to the third is 512. If I divide that by 2, I get 256. So remember what I'm doing is I'm actually adding these all up. So if you want to put plus signs in there. And so it's the difference is if we were just generating the sequence, we would just put commas between there and we would just be listing out the terms. And we would be done if we to find those. But because it's a series we're finding, we actually have to add these all up because they want the sum of all these terms. So I have one more thing to do. I'm going to take a second, pause the video, and use my calculator to add these up. And I got 647.5. So this sum of the terms, the second term through the 8th term is 647.5. And although there are lots of great problems on this page of the notes, they really are not different in any significant way from the ones that we've done. We might start at the 2nd and go to the 6th. We might, I think the only thing that is a little bit different is when you come down here to, say, 12 and 13 is now you're going to find out whatever this series is, the summation of these terms, and then we're going to multiply whatever we get by 3. So if there had been like this 3 in front of the summation and 10, I would have taken that 647.5 and multiplied by 3. So that coefficient really just affects it at the end. So this would just be simply finding that sum and then multiplying by 3. So no significant difference, and I feel like you should be well prepared to handle this first assignment on page 1 and 2. Thanks for coming to class.